welcome to AZ Academy USA. Today I'll be reading A Drop of Water. We are going to spend an hour today in following a drop of water on its travels. If I dip my finger in this basin of water and lift it up again, I bring with it a small glistening drop out of the water below and hold it before you. Tell me, have you any idea where this drop has been? What changes it has undergone? And what work has it been doing during all the long ages water has lain on the face of earth? Arabella B. Buckley, 1878. Water's smallest parts. A drop of water falls through the air. Down it splashes, breaking apart into tiny droplets. What would you see if you could break water into even smaller bits? No matter how closely you look, you can't see water's tiniest parts. Like other substances in the world, water is made of very tiny particles called molecules. On the pin above the smallest droplets contains more than 300 trillion water molecules. Pin, actual size. Water's elastic surface. Step by step, a camera reveals the curious changing shape of a drop of water as it falls from a spout. The water grows heavy and begins to fall. As it breaks from a strand of water, the drop shrinks itself into a tiny round ball or sphere. The drop flattens, then elongates as it falls. The strand, meanwhile, breaks into tiny droplets. The impact of the drops hitting the water causes a new strand to bounce out as another drop breaks away. Because water molecules cling to each other like tiny magnets, a drop of water can stay in one piece, even as it falls through the air. But the molecules at the water surface cling with a force that causes the surface to shrink. This force is called surface tension. When the surface of a drop of water shrinks to its smallest size, the drop forms a sphere. The sphere stretches because the water's weight and motion. The surface tension keeps the drops together, as if it were held in an elastic skin. Floating steel and wild waves. This steel pin seems to float magically on water. In fact, the pin is not really floating. It is held by the water surface tension. This works only if the pin is carefully lowered onto the water surface. Otherwise, the pin will sink. An eye that drops from above transforms the calm surface of water into a wild wave. Immediately, surface tension forms wrinkles in the wave, breaking the jets of water and shapes the smallest droplets into tiny spheres. When water meets air. A dry paintbrush is fluffy. The bristles of a white paintbrush cling together, but the bristles of a paintbrush in this jar of water are wet and fluffy. Why do the two wet brushes behave in different ways? The brush in the jar is held below the water surface. Water surrounds the bristles, but it has little effect on their positions. The wet brush outside the jar is surrounded by air. Water molecules don't cling to air, so they pull together and bring the bristles together too. Of the two wet brushes, only one outside the jar is affected by surface tension. When water flows up, gravity causes water to flow downwards, yet water has actually flowed up into these glass tubes. What could cause such strange behavior? Water molecules cling to materials such as glass with an attractive force called adhesion. That's why water drops cling to window panes after a rain. This attraction is also what causes water to creep up the sides of the glass tubes. The narrower the tube, the higher the water will climb. This behavior is called capillary attraction. Anywhere water creeps through the crevices, tiny spaces between grains of sand or fine vines in the stem of a plant, capillary attraction is at work. Soap bubbles. There are few objects you can make that have both the dazzling beauty and delicate precision of a soap bubble. Shown here at actual size, this bubble is a nearly perfect sphere. Its shimmering liquid skin is 500 times thinner than a human hair. Bubbles made of plain water break almost as quickly as they form. That's because surface tension is so strong that bubbles collapse. Adding soap from water weakens water surface tension. This allows a film of soapy water to stretch and stretch without breaking. When you blow a bubble, it looks somewhat like a drop of water emerging from a faucet. And just like the surface of a drop of water, the bubble's surface shrinks to form a sphere. Spheres and circles are mathematical shapes. Because they can form spontaneously, they are also shapes of nature. The circle below was formed instantly when the film inside the loop of string was broken. Bubble shapes. If you dip any wire film into a soap solution and pull it out, the wire edges will be connected with bubble film. The film shrinks, revealing the smallest possible surface area within the structure. When this frame was pulled out of soap solution, 12 panels of bubble film connect at the center of the frame. A straw was used to blow a bubble in the center. The 12 panels pulled the inner bubble into the shape of a cube. Molecules in motion. If a drop of water is added to a jar of still water, and if the water in the jar is not stirred, where will the new drop go? Will it stay near the top or sink to the bottom? A simple experiment reveals the answer. A drop of blue water enters a jar of clear water. It begins to split up. Parts of the drop sink and swirl in different directions. At last, the colored drop breaks into so many parts that it has become part of a whole drop of water. The molecules in liquid are moving all the time, pushing and pulling each other, attaching to and breaking away from neighboring molecules. The molecules in the blue drop break apart because they are pushed and pulled all over the jar by other water molecules. The energy that keeps the molecules moving is heat. This heat can come from the sun or the room in which the jar is standing. Without heat, water would not remain a liquid. Ice. When water cools, it loses energy. The molecules slow down and eventually stop swirling and pulling each other. When water freezes, the molecules lock together, forming a rigid structure. A drop of blue water no longer moves. The water has changed from a liquid to a solid. Ice. Ice is a solid, like metal or rock. But unlike metal or rock, ice is solid only at temperatures of 32 degrees Fahrenheit, 0 degrees Celsius, or colder. At room temperature, ice melts, changing back to a liquid. Water vapor. Water always seems to be disappearing from wet clothes on a line, from puddles on the ground, and from dishes on a draining board. We say it has dried up, but where has the water gone? Just as water can be liquid or solid, it can also be a gas. The water from the wet dishes evaporates. That is, it turns into a gas called water vapor. Molecule by molecule, the water from the drops of the wet dishes drifts invisibly to the air. Heating water in a kettle speeds evaporation. Heat from the stove makes the water turn to steam, which is extremely hot water vapor. When the steam hits the cooler air, tiny droplets form, and we see a cloud just beyond the kettle spout. Almost immediately, the droplets evaporate and change back to invisible vapor when the water molecules mingle with other molecules that make up the air. Condensation. The air around us always contains some water vapor. Water molecules move rapidly through the air and hit everything in their path. The molecules bounce off most warm surfaces, but stick to surfaces that are cold. In these photos, molecules of water vapor stick to the coldest part of the glass. Gradually, droplets form on the glass as the molecules accumulate. Water vapor changes from a gas to a liquid. That is, it condenses. Evaporation versus condensation. In the photographs above, why do the water droplets outside the glass disappear while the drops inside remain? Outside the glass, the water evaporates and spreads throughout the room as vapor. In time, the drops disappear. Inside the glass, water also evaporates, but the vapor is trapped. The air inside the glass becomes humid, which means that the air is full of water vapor, and that vapor condenses back onto the water drops as quickly as water molecules can evaporate. Therefore, the drops remain. Remove the glass and the vapor expands throughout the room. Evaporation continues, but condensation slows down. In time, the uncovered drops will disappear. How clouds form. Clouds are made of tiny water droplets too small to be seen without a microscope. If a cloud droplet is to form, water vapor must condense a particle of dust. Carried by wind, these dust particles are often bits of pollen, soot, soil, or salt. This experiment shows how cloud droplets form. Salt is placed on a jar lid above a dish of water. A glass cover straps to the water vapor. In minutes, the vapor condenses on the salt and coats each grain with water. Hours later, the salt dissolves and the water drops. Clouds form when water evaporates from the Earth's surface and rises into colder air. There, vapor condenses on cold, airborne particles. More and more molecules cling to the particles until droplets form. It takes about 1 million cloud droplets to make one raindrop. Rain does not taste salty or appear gritty because the particles that allow clouds to form are usually too small to be noticed in raindrops. This snowflake is shown 60 times its actual size. The angles between the 6 major branches are repeated over and over again in many of the smaller details of this amazing structure. How can such an integrated object form in the sky? Cloud droplets form when water vapor condenses or particles. But in very cold air, water molecules that cling to particles form tiny ice crystals as more water molecules from the air freezes onto the crystal, as they join at angles that allow a 6-sided structure to form. If the crystal grows large enough, it will fall to the ground as a snowflake. Clouds that reproduce snow often contain both ice crystals and liquid droplets. At the center of the snowflake is a cloud droplet that froze, allowing the snowflake to form around it. Scattered throughout, there are other cloud droplets that have frozen onto the snowflake as it fell through the cloud. Sometimes snow mixes with pellets of sleet, which are frozen raindrops like the ones shown below. By contrast, snowflakes are ice crystals that form when water vapor changes directly from glass to solid. Endless variety. Many ice crystals grow into shapes that are just tiny silvers, rods, or clumps of ice. Of these, the underlying 6-sided structure may not always be visible, but when weather conditions are just right, the crystals will grow into an astonishing variety of elaborate 6-sided designs. Look, I have a 6-sided snowflake. All the snowflakes on these 2 pages were photographed on the same day. All share the same equal lengths, but vary in design. One has 6 branches of equal lengths, giving the appearance of a 3-sided snowflake. Another snowflake has only 4 variations, like these are typical. Because different conditions of humidity, wind, and temperatures affected the growth of each snowflake as it fell, each design holds secrets of its unique journey to Earth. When a snowflake melts, its intricate design is lost forever in a drop of water. But a snowflake can vanish in another way. It can change directly from ice to vapor. The sequence below shows a single snowflake as it gradually disappears. Frost and dew. On some days when the air is humid, a sudden drop in temperature during the night will cause water vapor to condense on cold surfaces. By morning, the landscape is covered in sparkling drops of water. Dew. If temperatures fall below freezing, the cold weather relative of dew appears. Frost. On windows, frost forms tiny scratches and other imperfections on the glass. As with snowflakes, frost is the result of water vapor changing from a gas to a solid. That's why the angular structure of ice crystals is evident to the fern-like patterns of frost. When dew forms, a short walk through the glass will soak your feet. On spider webs, dewdrops appear like glistening pearls. In this photograph, we can see how water reflects and bends light. An upside-down landscape appears in each drop of water. Water and light. If you look carefully at this beam of light, you see the mysterious way in which light interacts with water. Some of the light is reflected, which means that it bounced off the surface of the water. But some of the light passes into the water. As the light enters the water, molecules bend the light or refract it. The bent rays of white light are transformed into all the colors of the rainbow. How is this possible? White light is made up of waves of many different sizes or wavelengths. The shortest wavelength, which we see, is violet, bends the most. Red, the longest wavelength, bends the least. All the other colors fall in between. Sun shining on spray from a garden hose creates a rainbow. The spray produces drops of water that bend the light and flash bright colors when seen from a correct angle. Natural rainbows work exactly the same way. The sun must be behind you and low in the sky. The arc of a rainbow is caused by the sun shining on billions of spherical raindrops that fill the sky. The water cycle. The sun's heat and the earth's gravity keeps water in constant motion. Water evaporates from puddles, ponds, lakes, and oceans, from plants and trees, and even from your skin. Water vapor moves invisibly through the air, but it's always ready to condense on a cool blade of grass or the surface of a pond. Massive clouds form as water vapor condenses on tiny particles of dust in the air. Then and only then can water fall from the sky as rain, replenishing lakes, rivers, and oceans. Hard to predict, impossible to control, water cycles around the earth. And water is precious. Without it, not a single living thing could survive. No plants would grow, not even one blade of grass. No animals will roam the earth, not even a spider. But somewhere in the world right now, snow drifts on a mountaintop and rain falls in a valley. And all around us, we are remain of the never-ending journey of a drop of water. Look, the water evaporated. Did you like this book? I hope you did. Please like and subscribe to my channel. Bye!